Before talking about giving example of the algorithm, so let me first finish this part. So we said that the basic algorithm use this much memory, right? Okay, but just let's simplify this because this is basically what log n plus 1 over epsilon. I mean, if you want to be a bit sloppy, then you can say it is a log n plus log m multiplied by 1 over epsilon, right? It's here. Okay? But in the final algorithm, you run k copies of this, right? K is this value. Okay, so it'll be log of 1 over delta. This is the final algorithm's memory usage. 1 over epsilon squared log n plus log m times the log over 1 over delta. Okay? So anyway, because he asked me just to give an example of the algorithm. So, I'll give a two example because it's a say it's like a 1, say 1, 2, 3, 2, 3, 1, 3, 4, 5. Okay. And then suppose this H1. Excuse me. We use the. I should have deleted this. I'm sorry. H decides slot, right? So suppose H1 is. I'm going to assume that this. I'm going to assume that K equals 3. So the table has 3 slots here, right? 3 slots. So I'm going to assume that H1 is 1, H2 is 1, H3 is 2, H4 is 2, and H5 is 3, right? Okay. And then say G1 is actually probably it would be nice to just assume. Let's do this. Okay. So what is G1? G1 is G1 is 1, G2 is 1, and G3 is minus 1, G4 is minus 1, G5 is 1. That's the first way. Okay, this is one example. So as I said before, so we are going to choose 2 hash functions, right? The first hash function will map an element, right, to one of the k slots. Okay, this is for mapping. Okay, and the g, another hash function g, will determine the sign of each element. Okay, and this was just one example. And suppose we have only like 5 distinct elements. Okay, there's 2 examples. Okay, so what's happening? So then, this counter table, right? It's a table, okay? So like I'm gonna read one. Okay, so before, so I'm going to put when I see element here, I'm going to put like this one like rod, one dot, okay? But I need to determine the slot. I find the slot, and I need to find the the sign, okay, left or right. So okay, I see 1, okay. 1 is mapped to the first slot, right? But the sign is 1, right? I'm going to put 1 here, right? But this comes from 1, so let's put 1 here, right? Actually, let me just put number here, right? Okay. And then I see 2 here. 2 also goes to the same slot, but it has same sign, okay? So 2 and 3. 3 goes to the second slot, but the sign is minus 1, right? So I put 3 here. I see 3 again. 3 again here. Right, 1 goes to here. 3 goes to here. 4 goes to what? 4 slot is second slot, right? But it's negative, right? So here, go here, and 5 here. Where's 5 go? 5 is what? Goes to third slot. any sign is here. And 1 goes to here and 2 goes to here. Okay. This is what's happening. So it's not a bad example. So let me try to change the example. I'm sorry. So let's just put this -1, right? Okay. So sorry about that. Then it'll be 1, 1, 2, 2, right? Okay. So what does this mean, right? So I like a 1. This is +3, right? And this is -2, right? This is -5, and this will be +1, right? Okay. So then, okay, what do I want to know? For example, I suppose I want to know the frequency of these 3, right? So it's this slot, right? So this, let's look at this C, H of 3, right? This is I want to look at this slot, right? And to recover the estimate, I'm going to multiply this guy's sign. Okay, this is -1, right? This is -5. This will be 5. Okay. So like basically this because 4, I have some noise. Okay, but if you believe that this 3 is a high frequency element, right? This noise will be kind of negligible, right? Because this 4 can go, I mean, think about other elements, right? The sign can be here or the other side, right? But they'll cancel off. Make sense? Any questions about the algorithm and memory guarantees? Yes.
What's the real world application of this algorithm?
Real world application? Oh yeah, it's used lots of times. Like for example, like think about Twitter, right? It's like you want to see like, oh yeah, so like think about like, how many times like people like express like some emotion, some events. You want to count it, but this tokens like the tweets are just huge, right? But yeah, you just want like make one just very fast pass, and then you just want to know like what's what you can, right? The data you want. So like counting stream algorithms are used extremely, it's popular, very common. It's kind of surprising that the algorithm is so simple, but elegant, but like the intuition and the analysis is not so trivial, right? Any more questions? Yes.
Okay, so the actual frequency of 3 is 4?
4, that's right.
So I guess I'm confused. Why are we doing an estimate? Can't we just count? Can't we just precisely know the frequency of 3?
Good question. Good question. So okay, if I know, okay, so if I know which elements are frequent elements a priori, I can only count those elements, right? So, but otherwise, here I have 2 like main goals here, right? I want to use a little memory, okay? You don't want to count every element like each, right? Because then you'll have to use what? The n times it, right? Probably like log m, right? Log m is the each counter can have m, can have value from 0 to m. So it can be, you'll have to use log m bits, right? But then you have like log n elements, right? So n times log m is just super big. I don't want to do this, right? So compare this to like this, right? M times log m. But now you have like log m, right? So it's a huge gain. So I mean, yeah, sure. If you have like a huge memory that kind of store everything, like we don't have to do all this, and this will be nonsense.
That makes sense.
Okay. Okay, so then now let's the remaining goals are to show these 2 properties, right? Good. So let me do this. It's a bit math, but I think it's kind of good to see how this math works. I mean, let's take away where we use the hash functions. Okay. Um, okay, the first one is kind of easy, so let's make it quick. So I want to, the first goal is to show that our estimate is an unbiased estimator. First goal, okay? So, see. So recall that we fixed A, okay? So X is our estimate of A, its frequency. So what is that, right? So what is F? Okay, so remember that this is nothing but, by the algorithm, we did this by GA times the count, right, at the place. So it was H, right? So what is this? Okay, so I need to define Yj. Yj is 1. Okay, so what are you doing here? So I want to see what's the counter in this, in the slot, right? So we're looking at this some specific, this is where, A is mapped, right? But many other items, elements could be mapped to same slot, right? So I'm gonna add up over all elements, right? Over J. And then, okay, remember that the algorithm was the, hey, let's add it whenever I see J. So I map to, I first multiply the sign, right? Gj. And then, okay, and then, it happens like fj times, right? Because this is how many times J appear, okay? But this only appears here, only when, if and only if, J and A, right, goes to same slot. So Yj is a random variable, okay, that it has a value 1, if and only if J and A are mapped to same slot. So this is exactly, this. Good. Okay, so then let's take expectation. So I'm going to separate this because so I'm going to separate. I'm going to take out A, right? Because A is the element of my interest. So it'll be G A squared times G, excuse me, F A, Y A. Let's just put just make it simple. Let's say this is J. Okay, I'm summing over all J other than A here, right? But then for A, I'm gonna have a J squared times because it will be G of A, right? FA times YA. Of course, this is 0 to 1, right? And this will be just 1, right? Also, right? So this will be just FA. Okay. So I'm interested in what is this value. Good. So what do I know here? So it'll be f a, excuse me. So expectation. Um, yeah, first of all, I can, I can use a linearity of expectation. Okay, so it'll be expectation of G of A, G of J, Fj, Yj. Okay. And everything is same, right? But what I know is this: these are determined by only function g. But what is yj? This is determined by another hash function h. Okay, so therefore, g and y, these two are independent. Okay, so what I'm going to have is that yj times expectation of ga, gj, e of yj. Right? And then now this is where we are going to use this linearity of expectation. From here, this g, h are independent. Okay. So far, I haven't used the hash function. Okay, the hash functions are being too universal. Okay. So what does this mean? So now I claim that actually you can also separate these. I'm sorry. This is I'm actually I'm sorry. Let's put this. Okay. So why is this true? This is because G in universal hash family. Okay, why? Think about two distinct elements, J and A. Okay, so if I explain the two universal hash family property in words, it means that if you think about any two distinct elements, the probability they go to like slash y in the table, they are completely independent. So pairwise independence. Therefore, you can separate this. Okay. So I mean, you know this, right? I guess I can use that. Let's use say AB, right? Suppose you have expectation of AB, right? If these two are independent, okay? We only need this independency between any pair of two distinct elements. This is what is guaranteed by two universal hash family. Okay. And what is this? Like this is 0, right? So you can have this can have either value 0 or 1. It's 0, right? It's also 0, right? So this will be 0. Is it good? Again, this is where we use the this is the place where we use the G being two universal hash family. Of course, G is a completely random function. This will be, you can separate this by, but we only need the guarantee that these two are independent, namely two universal pairwise independence. Any questions here? It's good? Okay, good. Yeah, now let's talk about the next one, the variance of x. Can I delete this? Okay, this is a bit pain, but so anyway, so what? So I mean, we argue that this is so what do you want to do? This if I write this here, this will be FA plus JA, GA, GJ, FJ, YJ, right? And this was we showed that this is E of x, right? Already. So then, what I want to know is this: the variance of x is nothing but the expectation of the square root of x minus ex. Okay. So it'll be okay. It looks like a big pain, right? But it's not that bad. So it's an expectation of ij not equal to a, which is GA, GA, GI, GJ, FI, FJ, YI, YJ. Okay? But this is easy, right? G is squared. This is 1. Not a problem, right? And then, okay, let's think about two cases here, right? So I need to construct every pair. Okay, the case 1. The case 1 is when I is not equal to j. Okay? Then what is this, right? Oh, by the way, here, by using linear expectation, I can just move this into here, right? Okay, so then, so what is this? E, G, I, G, J, F, I, F, J, Y, I, Y, J. Okay? Good. So what is this? Do you see this? Do you see this? What is 0? So F, I, F, J, these are determinants, right? These are fixed. And Y, I, Y, J, these are random variables, right? But these are determined by H, right? So it's basically the same logic, right? So it will be G, I, J, G, J. Actually, I put here F, I, F, J. Because anyway, these are constants, right? And what do we know here, right? Gi, Gj. Again, we can use pairwise independence because I and J are different. So this will be Fi, Fj, Egi, Egj. Right? This is 0, right? So the whole thing is 0. Second case. I equals j. In the case, what is this, right? Gi is same, gi, gj, right? So it's good, this is 1. And fi, fi squared. And yi, yj. it's same, so it's yi squared, right? Right? But y squared, this is 0, 1 random variable, right? So this is same as yi, right? So it's just nothing but e of fi squared times yi. Okay? So what's its value? Well, what is this? What is the expectation of yi? What is yi? The probability that J and A collide. Okay? How many slots we have? We have k slots. So we'll have fi squared divided by k. This is where we are using H being 2 universe. Right? Basically, I and A, these two elements, like they behave like random, independently. Therefore, the chance that they collide will be 1 over k. Okay, so remember that we use both, like, H being 2 universal and G being 2 universal. Okay, good. So then now it's quite simple, right? So what do we have here? So I only care about because when I and J are different, it's all 0. So I only care about when I equals J are the same, right? So it'll be what was that? It was fi squared by k. Okay. This is exactly 1 over k times f minus a added to small. Okay, that's good. Good. Any more questions here? Okay, so I'm going to cover another algorithm in this chapter. So, but before talking about other algorithm, I want to explain why this is called sketching algorithm. Like, remember that the algorithm was called. I don't remember. It was counting or counting. Was it counting? Count sketch. It's count sketch. Why is it called sketch? Okay. So actually, it's a very interesting property. So I'm going to explain. Okay, so why is this called sketch? I think I can delete everything because I don't need more. Why sketch? Right? It is a meaning. I mean, it sounds fancy, but it actually has a meaning. Okay, so let me formally define what this means. Like, okay, before I formally define this, what it means, but let me illustrate the sketch using this algorithm. Okay. So suppose remember the sigma denotes refers to the stream. Okay. Suppose the stream consists of 2 parts. The first part sigma 1 followed by sigma 2. Okay, I mean, you can split the stream into two substreams. Okay, and then suppose you run the same algorithm on the first stream. You can think of this effect, right? Because it's k-slots, right? And you can also run the same algorithm, but on the second stream, sigma 2. Okay. You can think of it as a vector 2 as well. But let's assume that we use the same hash functions, okay? Because otherwise it will be totally different. So let me put this H and G to emphasize that we're in this run and also in this run, in both runs we use the same hash functions. Okay. Then what I can observe is this. Okay. So, I mean, if this is your algorithm, right? This is a whole sequence, right? Stream, and you run the algorithm, you got this, counting, like kind of like compact counting. Okay. But now, but suppose you okay. So say like this is like 2 days. This is like day one, and this is day 2, right? But like okay, so you run the same algorithm yesterday, but this is sketch you have. Okay, but now you set a new sketch here. I mean, new data today, and then what you need to is that from the yesterday, you only need to know this. You don't have to run this whole algorithm from day 1 and day 2. Okay? Does this make sense? Okay. So if this doesn't hold, maybe you have to when you see the new data here, you may have to run the same algorithm from yesterday and today, right? But you don't have to. You only need to you are done. You are done with yesterday's data. You only need to remember this sketch. Okay. So you run the same algorithm with the same hash functions on today's stream, and then combine those two. Okay, so this is definition in the lecture note. Okay. Basically, kind of formalize what you're doing here, right? In this counting is this is just kind of data structure. You have like compact representation, what you have seen, and then so if you have 2 different data streams, what you can do is that you first apply you first get sketch it for the first input, and you can sketch it for the second input, and you can combine. Then that will be the same as running the algorithm on the whole stream. Okay? And then you may wonder, hey, is this kind of obvious like for all algorithms? Not necessarily, right? So the algorithm, Mr. Grimes' algorithm is not a sketch. So do you see why? So see, so you run like data one, so you have 2 streams, right? Day 1, day 2. You run like the Mr. Grimes' algorithm, right? Remember that the algorithm just what does it do, right? It kind of some like k, like m most k minus 1 k counters it with highly frequent elements, right? That's it. But what if they are different here? So you have like element 1, element 2, like element k. Excuse me. So like for day 1, like you have like some this E1, F1, E2. Probably it's bad notation. Sorry. So yeah, you have like K, like I guess K, maybe K minus one. It doesn't really matter anyway. So on by Ronda algorithm, you got like this K, like a distinct counts, right? Or like now, see, you like run the same algorithm on the second day input, right? Then maybe it'll be so like I don't know, so it'll be some different. So it'll be say like suppose these are totally different. Right? Suppose in day one and day two we see completely different sets of pretty frequent items. Okay, how can you combine these? Right? It's not obvious, right? So Mr. Grimes' algorithm is not a sketch. So not only like sometimes I mean the guarantee is actually not that bad actually. The problem is that it's if you see like new data, you may have to run the whole algorithm again, right? So sketching is actually very powerful like concept. Okay, so then let's go to the second algorithm. Any questions about this? Although I'm showing the math here, I mean, really, you need to catch the concepts here, like important concepts here, like the universal hash family, like why like this plus minus do, and then why do we using sketchy? These are very important concepts. Okay, so let me delete this. The second algorithm is kind of easier to analyze. Maybe conceptually also easier, but let me see. Okay, this algorithm is called count min sketch. We have the same problem, but it's different algorithm. Okay. I think I covered everything correctly. Okay. So what do you do? I guess I'm gonna show a picture here because So and every so like we are going to have t hash tables. So namely, we are going to have a t independent hash functions. Okay, all are two universal. So to guarantee to have to guarantee pairwise independence. Okay, what do we do? So when you see J, right? So like C, because we are going to use different hash functions, right? It can be mapped to for each table. It can go to it can be mapped to like somewhere here. Maybe it's J goes here and J goes here maybe, and maybe somewhere here, and like somewhere here, right? For every table, it'll go to it'll go to some place, some place. And like whenever C, like we just increment, excuse me, the counter. Okay, there is no negative counter here. It's only positive counter. Okay. So then what happens here, right? Like suppose so later like a different element arrives, right? Maybe these different elements can maybe this can maybe go to J prime, maybe also goes to here, maybe collide, right? Because we have many elements, right? But the k is small. But maybe for different for different table, like maybe you go to different slot. Okay. So anyway, okay, we have to count here also, count one, right? Yeah, maybe I should put like this one here because it's confusing. Sorry. So I have to put this one. Okay, then at the end of the day I have a count, right? So I have a counter for each hash table, and then for a query, what do I do? Let's look at for example J, right? So let's look at what's frequency. Okay, look at all the entries, and take the minimum. That's why it's called the minimum sketch. Okay. Is that algorithm clear? Okay, so I have two questions here. One, do you see this is a sketch? Okay, so you can just as long as you use you have the same hash functions, right? Then you have a counter for day one, you have a counter for day two. You can just combine them. You can just add up, right? So this algorithm is actually sketch. Okay, second thing. So what is the memory use? Like what? Okay, for sure this is one pass algorithm, right? And what is the memory usage now? Okay, what do we have here? We have so by the way, we have a k times t counters, right? And each can have value up to m. So we'll have to use in the worst case log m bits, right? This is for counting. Okay. And then what about the hash functions, right? So recall that if the universe size is n, to get a universal two universal hash family function, so you need log n, log of the universe size bits, right? So you have t functions, right? So it'll be t times log n. That's it. So if you're okay with being sloppy here, it's m plus k times t times log m plus log n, right? Yeah, k is what? K is I mean this. So this is be 1 over epsilon, and this log 1 over delta I times log n plus log m plus log n, and let's put one, right? That's memory usage. Okay. I'm going to compare this to other algorithms later, but anyway, this is it. This one here, okay? And we are going to show the following claim. The probability that this is our main claim. Let me explain away what these mean. As before, epsilon is a kind of an accuracy parameter you can control. And like f minus a, this is L1 norm, right? So this is just nothing but the whole thing, the minus of everything minus f a. Okay? L1 norm is knocking out a's frequency. So, and delta is the success probability, right? Like the probability, the parameter that governs success probability. Okay, so the first one, this should be obvious. Do you see why this is true? This should be obvious. In other words, the first claim means that it means that we only overestimate. You see? This is why? Because why? I mean, if there are no, okay, suppose we only have an item j, right? Element j. Then of course at the end of the day we'll get the correct answer, right? But if you see like more elements, right? They can only add more. Therefore, I may overestimate it, but I'll never underestimate. Okay. No underestimate. Right, that's one thing. But here, okay, so let me ask a question here. Is this an unbiased estimator? Unbiased means that when you take the expectation should be the same as the true value. Do you agree or not? This cannot be, right? This cannot be. In the count sketch sheet, like you use plus minus 1, right, to cancel off, but we don't do that here, because like when you see like more items actually you may have some you can have some overestimate, right? So the average will never be for some items the average will never be the same as the true value. It's not unbiased estimator. Okay. But then you may wonder, hey, why is this algorithm, right? But I don't know if you remember this, but you know. So I'm gonna go over this again later, but like in the count sketching, the memory usage was like something like this, right? 1 of epsilon squared log 1 of delta times log m plus log n, right? So you have to use a 1 of epsilon factor more memory in the previous algorithm. I mean, this epsilon is pretty actually big, you know. It's not joke. It's like if you want like 1% error, right? So then you'd have to use a 1 factor more memory, right? Of course, it's not completely comparable because you see this, you know, this is based on L1 norm, right? But in the previous algorithm it was L2 norm. So it's not completely comparable, but you know, there's a reason why this algorithm is interesting.